Topic 2.12 is all about logarithmic function manipulation, which is how we can add and subtract or combine logarithms to make them simplified, to write them in simplified form. These rules follow exponent rules. So if we remember our exponent rules, we actually know our logarithm rules at the same time. So I'm going to apply these towards our exponent rules. The product property for logarithms, it tells me that if I am multiplying inside one argument, inside one logarithm, I can separate them by adding. And my friends, that's the same rule that we have for bases, for power rules, which means that if we are multiplying, we add those logarithms together. If we are multiplying bases, we add the exponents. If we've multiplied inside a logarithm, we add to separate. So for example, if you see log base 2 of 5x, that's 5 times x, yes? So I can separate that into log base 2 of 5 and log base 2 of x. I separated it with I separated multiplication with addition. The second rule is called the quotient property that says if we are dividing two things inside of a logarithm, we can separate it with subtraction. Divide means subtract. So for example, log base 3 of y over 4, we can separate by log base 3 of y minus log base 3 of 4. Bless you. The last one is called the power property, the power rule. Just like with exponents, if you have a power raised to a power, you multiply those powers together. So if you have a logarithm with a power, what you're going to do is you're going to take that power and you're going to drop it right in front of the logarithm so that it is multiplied, which means we have power to a power means multiply, or argument to a power means multiply. These mad spam rules are the same mad spam rules we use for exponents. And that makes sense because exponents and logarithms are tied together. They're inverses of each other, so these properties are inverses. Now, what we're going to be doing today is, I guess I should go over this example. Log base 7 of 3 to the x. These don't cancel out because they're not the same number. But we can take that power x and drop it right in front. Now, I do need to make a note right here and make sure you know this. This is like a little note to self. Log base 7 of 3 to the x is not the same as log base 7 of 3 to the x. Do you see how that's different? If you have the second one, that is not the power rule, not the power property. This is when specifically the thing inside the logarithm has a power, not when the logarithm itself is raised to a power. Do we see that difference? Fabulous. So our job today is to be able to manipulate these logarithmic expressions and write them in different formats. Eventually what happens is that these properties allow me to relate one logarithm to another using transformations that we learned back in Algebra 2 and earlier in this class, and find that various transformations of logarithmic functions can be written in multiple ways. A horizontal dilation of a logarithm is going to be similar to a vertical translation. This sounds familiar because it's what we did with exponential functions earlier in this unit. But before we get to all the transformations, let's just make sure we understand how to manipulate these logarithms. We're going to condense them down to one logarithm, which means we're going to use all of these rules backwards. So if you see a plus sign, what should you do with those two things? If you see a minus sign, what should you do? And if you see a number multiplied in front of a log, what should you do? Move it to make it a power. Perfect. That's what we're going to do. Let's look at this first guy. What do we see here in these two logarithms?
Addition.
Addition, which means if I want to condense them down to 1 or simplify them down to 1, what am I going to do with the x and the y? Combine them by doing? Multiplying. So when I condense these down to one logarithm, I have log base 4 of x times y. Now, we don't typically put the little dot there to show you we're multiplying. We would just say xy. But since these are our notes and we're learning, let's put a little dot to make sure we know they've been multiplied. That's it. Did the base change? No, the base never changes. Fabulous. What about letter B?
Divide.
We're going to be dividing these two. What will go in the numerator, the 5 or the z? The 5. If the logarithm itself is positive, that number goes in the numerator. If the logarithm is negative, that number goes in the denominator. So this would become log base 3 of 5 divided by z, where again, my divide, because I subtracted the two logarithms separately. Feel good? Now remember, I just said this, I'm going to say it again. If the logarithm is positive, that part goes in the numerator of the argument. If the logarithm is negative, it goes in the denominator. And that's important because if we see something like this, we have two minus signs. But if we just,
Log is positive.
if the log is positive, that goes in the numerator. If the log is negative, it goes in the denominator. So how many parts will I have in my denominator? 2. Here's what it's going to look like. It's going to be log base 10, which yes, it's just a common log. You don't have to write the 10. Of x divided by 5z. Whoa. The 5 and the z are multiplied in the denominator, which feels weird. But because we're subtracting those two logarithms, we put them both in the denominator. Yes, ma'am?
How do you know that the 5 and the z are negative? Does the subtraction sign make them negative?
Correct.
Okay.
So subtraction is like, it is a negative property of that logarithm. I could say plus negative, but we just use one. So we just use minus. Whatever logarithm is subtracted or is negative goes into the bottom. Good question. Can I start to make it a teeny bit more complicated? Because so far, if you notice, what color have we not used that was in our chart at the top? Green. Here's where we start to use the green, and green has to be done first. If you are condensing logarithms, green has to go first. So we always will now look in front of the logarithms for a number. Don't care about the sign, just a number. Does one of these logarithms have a number in front of it? This one, right? Where does that 3 go? To the power. Now, it goes to the power of the exact log it's touching, meaning I'm only going to move it, bow, right there. That's it. That's the only place it goes. So this becomes, in this first step, log base 2 of x to the 3rd power minus log base 2 of y. That's all I've done so far. That property gets its own step, if you will. But now that there are no more numbers in front of these logarithms, I can combine them down to 1. What's in between these logarithms?
The minus.
And what do I do with minuses?
Divide.
Divide. So this becomes log base 2 of x cubed divided by y. And there's my final answer. We always take care of the green power property first, then we can do the product and the quotient. For letter E, do any of these have a coefficient in front of the log, a number in front of the log?
2. 2 and 5.
2 and 5. Thank you for not saying negative 5. It's just the number. I know that that's minus 5 times the log, but we're just going to minus 5 log, if that makes sense. So both of those we can take care of in my first step. So we're going to go bloop and bloop. We're going to drop those numbers as exponents up at the top. This becomes log base 7 of a squared minus log base 7 of b to the 5th plus, and then we just drop this one down, log base 7 of 4. So far all I've done is taken care of this and this. You notice how so far all of these have the same base? Like in every problem we've done, it's like the logs have the same base. They have to for us to combine them in this way. I'm just making that note. Okay, but now I have a whole lot going on. What do you see that separates these logarithms?
Minus sign.
A minus sign and a?
Plus sign.
Ooh, interesting. Earlier I said that negative logarithms go where?
Huh?
In the bottom.
The bottom. And where do positive logarithms go? How many positive logarithms do I have here?
Just one,
2.
We have 2. Because this first one is positive and the last one is positive, which means you're going to have 2 pieces in your numerator when we combine this down to 1 log. This is log base 7 of a, let me write it better, 4a squared divided by b to the 5th. You could say a squared times 4. That's mathematically equivalent, but we don't normally say things that way. We're going to put the coefficient first. And again, just to make sure we know where this came from, we're going to put a little dot to show we are multiplying the 4 times a squared. These are our notes so that we remember where it went, where it came from. We do this. So far, so good? Again, I want to make this point known. Do you notice that in each of these problems, when we were combining these logarithms, they had the same base? We see that? That's important because what do you notice about this last one? One of them doesn't even have a log. But to combine them down, the expressions, down to a single logarithm, I need them to have a logarithm with the same base. So what I'm going to do is I'm going to give the, you know how when you make like fractions have a common denominator, right? And if they don't, you just multiply them by something to force them to have a common denominator. We're going to do the same concept, but with logarithms. So the logarithm that I want to be here, I want this to have a log base 6 of something next to that 2 so that that term has a log base 6. But I can't let it be anything other than the number 1 because then I'm not changing this problem at all, the same way you need to gather common denominators when you're dealing with fractions. So what number can I put in that parentheses that would make this log base 6 of something equal to 1? Log base 6 of 1 is equal to 1? No. Not 0. You can't put 0 in a log. What number can I put right here so that this is 1? 6 raised to 1 power is 6. If we do log base 6 of 6, wouldn't that like cancel out? It's because it's equal to 1. So I've multiplied this first term, the 2, by 1, as if I'm finding a common denominator. Log base 6 of 6 is 1. But now, do you notice that the first term and the second term have the same logarithm base? Now we can do some manipulations. First things first is I notice, because I do my green step first, that this logarithm has a number in front of it. Where does it go? To the power of 6. Very good. Which means, what is 6 to the second power? 36. That entire first logarithm becomes log base 6 of 36. Then I have my plus log base 6 of x. Just as a double check to make sure we didn't change this problem at all. 6 to what power is 36? That's what we started with, right? We've not changed this problem at all. We've just shown an equivalent form of it. But now I see we have this plus sign, and we can combine logarithms together to have plus signs by multiplying them. So this would be log base 6 of 36 times x, or 36x. But I'm going to show the little times because these are our notes and we're learning. So a question like this may appear on one of your FRQs for this class, but logarithms are a hot topic, a hot commodity, if you will, when it comes to multiple choice questions for our AP exam. Here's an example of what these sorts of questions might look like. They're not hard. This one says, which of the following expressions is equivalent to log base 3 of x squared divided by y? If we're using our properties, we should be able to eliminate this down to only one answer. My first question for you would be, what symbol in between these two logarithms should I have, a plus or a minus? a minus. So which one of these answer choices can we get rid of? D, get rid of it. So you're telling me at this point, by saying that would happen, that we'd have log base 3 of x squared minus log base 3 of y.
There can't be numbers in front of it.
Say again?
Can't be numbers in front of it.
If we're condensing it, correct, but if you'll notice, all of these look expanded. So what if we use the rule to expand instead of condensing it? Where would this 2 go if we're trying to fully expand this? Yeah, Kim's doing this with her hand. She says to the front, like this. Is this what you mean? Nice, which means this would be 2 log base 3 of x minus log base 3 of y. Which answer choice is correct? C. So Shane, you're right. The 2 cannot be in the front if we're simplifying. So if it would have been easier for you to start with the answer choices and work backwards to the question, totally do it that way. I like that idea. But that's pretty simple, right? If you know my 3 rules. Multiply, add, divide, subtract, power to a power means multiply. So here's where it gets confusing. The other type of question that can be asked about these logarithms in multiple choice has to do with how they're related to transformations of functions. Number 3 says the function f of x equal to log of 6x is a horizontal dilation of the function g of x equal to log x. This makes sense. Horizontal dilations happen inside the function. Where is this 6 multiplied right now? Inside. So it's a horizontal dilation. Check, check. Show that f can also be written as a vertical translation of g. Vertical translations, where should that be? Inside or outside? Outside. Vertical transformations are outside, where there's some number we're adding. So we need to manipulate, using my 3 rules, this beginning function to show what we are adding or subtracting from the function. So if we grab that first function, the f of x function, we notice that this is log of 6x, which means 6 times x. How do I separate, instead of simplify, how do I separate something that has been multiplied on the inside? Multiply? No.
Wait, what was the question?
If I'm multiplying on the inside, how do I separate it on the outside?
Divide.
Adding. Multiply, add. Divide, subtract.
Oh,
Power, multiply. So we're going to do this. We're going to say, all right, this should be equal to log base 6, log of 6 plus log of x. And at this point, if we notice, we already answered the question. What? It asks me, what have we added to the regular function log of x so that it's a vertical translation? Here's log of x, right? What have we added to it? We've added this right here, right? That means that this is my vertical translation. We would write the following conclusion sentence. This would maybe be a multiple choice question, by the way, so we would read the following sentence, but it might say something like this. It might say f of x is a vertical translation of the g of x function up log of 6 units, because we are adding that. And if we were to put log of 6 in our calculator, it would be approximately 0.7782. So we've moved this graph up 0.7782 units. So again, just because I see the question mark faces among you, so let me do it one more again. Did you follow how I went from this to this? Yeah, multiply means add. After that, what it's wanting us to conclude is how this has translated the parent function graph log of x. So if I were to just look at log of x, I have changed log of x by adding log of 6. which is a vertical translation. The next property I'm going to introduce to you feels wrong because once we started introducing the idea of bases, has the base ever changed?
No.
Should the base ever change? Unless you are using what's called the change of base property. We never change the base of a logarithm except for this one instance. The change of base property really came from and was really useful before calculators got smart enough, because there didn't used to be a log base button on your calculator. So we used to have to use, and by we I mean I, as a student, used to have to use this property to evaluate any logarithm other than base e or base 10. You guys are lucky. There's a log base button now. So now the change of base property is really helpful when we're talking about these dilations again. The change of base property basically says, and we're going to highlight this very specifically, it says that if you have log base b, that's purple, of x, that's orange, we can evaluate this by changing the base of two separate logarithms and putting the x on the top and the b on the bottom. So log base b of x can be evaluated by log of x divided by log of b. Yes. Yes. It doesn't matter what base you pick here or here, as long as it's the same. So back in the day, to evaluate a logarithm, we'd use 10 or e because there was buttons on our calculator for that. Regular log and natural log. But for us in this class, now that it's 2025, we can have a different use of this change of base property. The use for this change of base property is something like this. It allows us to illustrate that all logarithmic functions are vertical dilations of each other, because we can rewrite them with a different function multiplied them, not function, constant multiplied by them. Observe. We're going to let f of x be log base 4 of x, and we're going to let g of x be log base 9 of x. We're going to show that this function f of x is a vertical dilation of g by finding the value of k such that I can multiply it by k and have g. Stay with me. So let's write down f of x. F of x is currently equal to log base 4 of x. But I want this to have a base of 9. Why would I want it to have a base of 9? I want it to have base of 9. So what I'm going to do is I'm going to use the change of base property and force my base that's on the top and the bottom, the a if you will, to be the number 9. So I could rewrite this as follows. Let me use some color to show you what I'm doing. Here's my 4. Here's the x. I'm going to rewrite this as log base 9 of x divided by log base 9 of 4. That is using the change of base property. I specifically chose to use the base of 9 so that f and g could be related to each other. Now, if you notice, log base 9 of x, isn't that what I have written right here, right now? Which means I can rewrite this as g of x divided by log base 9 of 4. Further, I could rewrite this as 1 over log base 9 of 4 times g of x. And the reason I wanted to do that is because in the question, it asks me to write an equation exactly like that. Something times g of x. Here's my something multiplied by g of x. So we have taken a logarithm with a base of 4 and changed it into a logarithm with a base of 9. We can do that by multiplying it by this constant, 1 over log base 9 of 4. I know that those concepts are hard. So to get some good vibes back in here, I've got one more question for you to answer on your notes that we're going to look at. It's going to remind you that you do actually know what's going on here. In example 5, it says which of the following expressions is equivalent to 3 natural log of x minus 4 natural log of y. This one's for you. I'm going to give you a few minutes, like 1 minute. I want you to answer this question. So here's what I'm seeing on your papers. I'm seeing that a lot of us noticed, going back to what we learned at first, that we have numbers in front of these logs. Where do they go? To be exponents, to be powers. So this is natural log of x to the third minus natural log of y to the fourth. And then we're subtracting these guys. So what do we do to combine them together? Divide. So this is natural log of x to the third divided by y to the fourth, which means which answer choice did you pick? Very good. Okay, so look, I know that there was a moment of hardness in here when we were talking about the transformations, but for the most part, do you understand the concepts of manipulating these logarithms? Okay. Thank you so much. You guys did great today.